Now we're going to talk about variable types in C, specifically integer types. So in C89, the standard supports 4 integer types: a char, a short, an int, and a long. Right? So what's the difference between these? When you make a choice between one of these 4, what you're choosing is how much memory will be devoted to representing numbers of that type. Right? So in the standard, it says that a char is 1 byte, which is 8 bits. A short is at least, so greater than or equal, 2 bytes. An int is at least 2 bytes. And a long is at least 4 bytes. And so if you look in older C books, you'll even see that they'll tell you an int is 2 bytes, which I guess it was at some point in the past. In modern computers, though, what you'll typically find is that an int, so I'm writing this in 2020, you find that an int is 4 bytes and a long is 8 bytes. And in order for this to be true, that this is 8 bytes, you need to be using a computer in which addresses are 64 bits. Which are 8 bytes. On your particular computer, you can figure out how much memory each of these represents. If we're on, over here on Linux, if I look at the file vim, and I had to track this down earlier, if you look in the limits.h file, and this is where it's at on Linux, so on Windows it'd be somewhere else. If I go to the top here, you can look at what the upper and lower ranges are for various values. So here it tells me that a char is 8 bits, which is 1 byte. Down here it tells me that the maximum value for an unsigned short, and we'll talk about what unsigned means later, but it tells me the maximum value of this is 65,535. That means that a short is 2 bytes. It says here that the max value for an int is this number, which is a little bit over 2 billion for the upper range. And if you're representing it as unsigned, it's a little bit over 4 billion. So this is 4 bytes. And then a long can represent numbers up to this value, which is 8 bytes. So those match up with what I told you earlier. Because once again, we're in 2020 and we're using more modern values for things. So why do we care about this other than, you may have a situation where you don't want to waste space. But in terms of why you choose one of these over another, the number of bytes ultimately tells us how many different bit combinations we have. So number of bits, which is what each of these ultimately is, right? Because 1 byte is 8 bits. Number of bits corresponds to number of bit patterns. So for example, if I have 2-bit numbers, and there is no such thing here, but I'm using something I can write out, 2-bit numbers or integers. Well, then the bit arrangements are 00, 01, 10, and 11. So this right here is 2 to the square root equals 4 bit arrangements. If I had 3 bits, then I'd have 2 cubed equals 8 bit arrangements or patterns. The importance of that is if I have 4 arrangements, well, then that means I can represent 4 distinct values. If I have 8 arrangements, I can represent 8 distinct values. So that's the reason why 4 bytes, which is 32 bits, has about 4 billion different arrangements. So there's about 4 billion different numbers I can represent. What those numbers are depends on, to some degree, on whether or not you're trying to represent negative numbers or not. All right? So Each of these, if you just write as is, so if I do this, if I declare a variable as int x equals 42, if I just write int alone, I'm automatically getting a signed type, which means I can also represent negative numbers. Now, this is the default. For each of these, if I write char something, short something, int something, or long something, it's automatically a signed type, so I don't really need to do this. However, I could also do this, unsigned int, say z is equal to 75. Now, by writing this, I'm saying z cannot represent negative numbers. But regardless of which of these I choose, I still have a certain number of bit arrangements that I can use. It's just that in this case, all those bit patterns are devoted to representing non-negative numbers. And I'm saying non-negative instead of positive to indicate I'm including 0 as well. This can represent positive, negative, or 0 numbers. All right? But they still both have the same number of bit patterns. It's just now approximately half of these are devoted to negative numbers. Over here, they're devoted to 0 and then all positive numbers. So let's look at this first, because this is closer to what people think when they write out bit patterns, and see what we have. So for the sake of this example, let's assume we have a 3-bit integer type. All right. And we already said that means I have 2 to the third equals 8 bit patterns. So those bit patterns are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So these are the binary numbers. And then their decimal equivalent, base 10, are 0, 1, 2, 3. And then for these, 4, 5, 6, 7. So I don't ever make it up to 8 here because I start counting at 0. So I'll make it up to 8 minus 1. That's my upper bound. So whether I'm talking about 3-bit numbers or 64-bit numbers or whatever, this is how this works when we're talking about unsigned integers. Right? I have 8-bit patterns, but all those are devoted to either positive numbers or a 0. So what about unsigned? Let's talk about how that works. When you're writing numbers on paper, like in a math class, when we want to represent a positive number, typically we leave off the plus sign, but I could do this, plus 41. But if I want to represent a negative number, then we do include the sign. And I might say negative 55.63. So here's the sign. So how do we represent signed numbers in our computer? Well, we don't have actual symbols, plus or minus. So instead, what we do is we use one of the bits for that variable as the sign bit. So if I say this is a char, and I say char C, I'm allocating 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. This right here is the sign bit position. And in each of those integer types, the leftmost position is called the sign bit. So when we're talking about sign types, 0 in this position is equal to the number 0 or a positive number. And therefore 1 means it's negative. So how do we represent negative numbers? That's not as obvious as you think. So there are 3 forms of, or 3 ways of representing negative numbers that I'm aware of. Those are called signed magnitude, or some people write sign/magnitude. So these are ways to represent negatives. Negative integers represent negative. So it's 1. Another's called 1's complement. And then 2's complement. Just to jump ahead, I'll tell you most modern computers use this. So most of our discussion will be based upon this. But let's see the differences between these. So if we're talking about signed magnitude, this is the closest to the way we think about it when we normally write numbers. When I'm normally writing a number, if I say the magnitude of the number is 3, if that happens to be a positive 3, I just put a plus in front of it. And if it's a negative 3, I just put a minus in front of it. But I still wrote 3 in either case. So in signed magnitude, we have a bit pattern representing, say, a 3 that would be the same, and then I either put my 0 in front of it to indicate non-negative, or 1 to indicate negative. So for example, if I have a 3-bit integer, a signed integer, and I'm using signed magnitude representation, I say, okay, positive 3 would be this, because if you don't know how to read this, go back and look at my video on bits and bytes and number bases. But this is 2 plus 1 is 3, and then to get negative 3, I put a minus sign in front of it, and I still have my 3. So this is how this works. 1's complement looks like this. To represent non-negative numbers, it's the same. So positive 3, if I'm using a 3-bit integer type, would be 0, 1, 1. But to get negative 3, what I do is I flip the bits. And what I mean by that is I turn each 0 into a 1 and each 1 into a 0. So in this case, what I would have would be 0 becomes 1, 1 becomes 0, 1 becomes 0. So this right here is negative 3 using 1's complement. And then finally for 2's complement, the non-negative numbers, once again, are represented the same way. But to get 2's complement, first I perform the operation to get the 1's complement value. That is, I flip the bits. So this is a two-step process. Flip the bits, then add 1. So flipping the bits will give me 1, 0, 0, and I add 1 to that, and I get 1, 0, 1. So here's, all these have the same positive representation for 3, positive 3, excuse me, 0, 1, 1. But here's the signed magnitude answer. Here's the 1's complement answer. Here's the 2's complement answer. So let's create a little table and see the numbers next to each other. So the bit pattern. So let's do, say, 3 bits, 3-bit numbers. So my bit patterns are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. If I'm using signed magnitude, let's draw some more lines to keep things lined up. So this is 0, 1, 2, 3, and that's going to be the case in each of these. 1's complement. Two's complement. So what did we say we do for sign magnitude? So the leftmost bit is the sign. So here we have positive 0. And so this right here is negative 0. Believe it or not. So this is really positive 0. And this is 1. This is negative 1. 1, 0 is 2. So 1, 1, 0 is negative 2. And 1, 1 is 3. So 1, 1 is negative 3. 1's complement says we flip the bits. So once again, we're going to say this is positive 0. So all zeros is positive 0. All ones is negative 0. 0, 0, 1 is positive 1. So 1, 1, 0 is negative 1. 0, 1, 0 is 2. So 1, 0, 1 is minus 2. And then finally, this right here should be minus 3. So both of these types represent positive and negative zeros. So what about 2's complement? We could go through the process I told you, which is flip the bits and add 1. But when I'm creating the table, I always think of it this way. In 2's complement representation, the bit pattern consisting of all 1s is negative 1. And then I just work backwards from there. So what can we note about these different ways? All 3 of these represent 8 different numbers. However, in these 2 we have plus 0 as well as negative 0, or positive 0 and minus 0. 2's complement represent 8 distinct numbers, but now they go 0 to 3 on the non-negative side and minus 1 to minus 4 on the negative side. Neither of these can represent negative 4 using only 3 bits. It would take an extra bit to get to that. All right? So most of our discussion, once again, will focus on 2's complement because that's what most modern computers use. So what's the range of values that I can represent? If we're using 2's complement, if we look at the values here and try to recognize some patterns, and we'll say B equals number of bits, then if it's unsigned or signed, we'll produce a table here. So we said that if we were talking about unsigned numbers, the minimum value was 0. So it went 0, 1, 2, 3 when we had 3 bits. But then we kept counting, right? We went 4, 5, 6, 7. So the minimum here is 0. And what is the max? Well, the numbers would have been 0, so this would be 2's complement unsigned. 0, 1, 2, 3, 4, 5, 6, 7. Notice here 7 is equal to 2 to the third minus 1. So we have 2 to the third bit arrangements, but since we start counting at 0, the maximum number doesn't make it to 8, it makes it to 8 minus 1. So this is 2 to the b power, and then subtract 1 from it. But what about the sign type? Well, our minimum number is some negative number, and here it was minus 4. So what's the relationship between minus 4 and 3 bits? Well, 4 is equal to 2 squared. And the power of 2 there is 3 minus 1. So it's really negative 2 to the b minus 1 power. 3 minus 1 is 2. 2 squared is 4. Negative 4 is my smallest number. And then my maximum sign number, here which is positive 3, is going to be 2 to the b minus 1 power, and then subtract 1 from all that. So that's what we get. All right? So once again, the issues here are, come back and look at this. When I make a choice, so if I say char, which is 1 byte, what is the range of values I can represent? So let's write those out. So we said that a char is 1 byte, which is equal to 8 bits. A short is at least 2 bytes. And on modern computers, they are 2 bytes. That's 16 bits. An int on modern computers, let's do all these on modern computers. So this will be equal here. This will be 4 bytes, which is 32 bits. And a long is equal to 8 bytes, which is 64 bits. So if we're talking about unsigned types, then a char has 2 to the 8 bit patterns, and I get the 8 from here, and the range then is going to be 0 to positive 255. 2 to the 8th is 256, so I'll start counting at 0 and work up to 255. All right. If I'm talking about a short, then we have 2 to the 16th bit patterns, which is a little more than 65,000. And so that means we have from 0 up to about that. An int can represent approximately 4 billion values. And then a long is 260 or 2 to the 64th bit patterns, whatever number that represents. It's really big, right? Now, what if they're signed? Now, technically, the standard, so the ANSI standard, the C89, doesn't specify how to represent negative numbers. Or negative integers is really what we're talking about. Which means if you had a computer that stored negative integers using 1's complement, then if it was a char on that computer, on a 1's complement computer, then the range of values would be minus 127 to positive 127. Because remember, we were looking at this example over here. We saw that because we have both a positive and negative 0, then in terms of magnitude, we only got up to 3 in both directions, positive 3 or negative 3. Whereas for 2's complement, we can actually get up to 3 or negative 4. So we can get up to 3 on this side and 4 on this side in terms of magnitude. Forget the sign. But in this case, they'll match. So a char on a 2's complement computer can represent minus 128 up to positive 127. These still add up to 256, which is my 2 to the 8th number of bit patterns. But this is the range of values. And the others work in the same way. So if we're talking about a short on a 2's complement computer, put it here, short on 2's complement computer, minus 32, 768 I think is the number, and positive 32, 767. In fact, we can check. Let's go back and look at the limits file, and it will tell me the answer to this actually. So what was the value? 32, 768, negative 32, 768, and positive 32, 767. And for the ints, minus 128 to 127. So it does match up with what I have here and here. All right. So those are the decisions you have to make. So when you're deciding what to do, if you're trying to represent something and you said, for example, I have these requirements. Save space to represent integers in range of minus 75 up to positive 300. Well, can I use a char? Well, if we're talking about 2's complement, here's my range, minus 128 to positive 127. Minus 75 will fit here, but 300 is too big for this, so this is out. So I go to short. Minus 32,768 to positive 32,767. Certainly this will hold up to minus 75, and this holds up to positive 300. So this would be what I would choose in this case. That's why we care. All right? So I think that's most of what we need to know right now about integers, and I'll make a separate video for floating point types.